So probably we should start. Good afternoon, good evening, everyone. I'm your chairperson, Gregory Vereshchagin from ICRANet. And now we're going to have a session, afternoon session of the conference with the talks on gamma ray bursts and on the role of general relativity for elementary particle physics. And it's my pleasure to introduce Professor Shahram Abbassi, who's going to speak about black hole hyperaccretion disks and gamma ray bursts. Well, you can speak for 25 minutes, and we will reserve last 5 minutes for questions, if it's okay with you. So you may start, please.
Hi, everyone, and thanks for the organizer to give me this chance to present my recent research line. I'm wondering that why this is by chance or just by arranging that the many people today talk about GRB. I'm talking about GRB in the point of semi-analytical method to modeling a central engine of GRBs. This work was started from last 3 years ago by collaboration with my postdoc Narges Shahamat and Professor Tong Liu from Xiamen University, and we could publish 3 papers. At first, I should start to review GRB properties. GRB is the brightest and the most energetic events known to occur in the universe. Bursts can last from the millisecond, 10 milliseconds to several hours. After the initial flash of GRB, a long-lived afterglow is usually emitted at longer wavelengths. So it's very important for physicists to prepare to introduce reliable model for this kind of events. The rate of occurrence of GRB is 10 power minus 6 per year per galaxy. And normally, in average, we have 1 GRB events per day. Some remarkably results from the observation we have from the gamma ray observation. No 2 gamma ray burst light curves are identical. There are a wide variety of variation in time structure and duration and any properties of GRB. However, 2 classes of GRB have been proposed: short gamma ray burst for less than 2 seconds and long gamma ray burst for more than 2 seconds. Normally, long gamma ray bursts are observed in the star-forming galaxies with redshift up to 25 to 30. So it's results in agreement with the collapsar model. And the short gamma ray bursts, seems to be less regular. However, the redshift distribution are more similar to the old object population. This result is also inconsistent with the merger model. The GRB's spectral feature, the most and dominant feature is the prompt emission, which is just the first emission comes from the GRB. It consists of soft gamma ray and in some time X-ray emission. The time duration is less than 2 for short gamma ray burst and more than 2 seconds for the gamma ray long gamma ray burst. Also, we have afterglow. This afterglow is part of a spectrum is considered low energy emission and in some band pass, optical band pass and other band pass of wavelengths. After in the afterglow, we have some feature as X-ray flares, X-ray activity. X-ray afterglow is the light curve consists of 5 time main parts: steep decay phase and shallow decay phase, normal decay phase, post-jet break phase, or even X-ray flash. X-ray flash is very important for us because we are trying to modeling X-ray flare of GRB. They are appear as ups and down in X-ray light curves. It's widely accepted that they are powered by late central engine activities. optical afterglow and the radio afterglow. And there are several evidences, observational evidences that we have some optical wavelengths in the afterglows, and in some part of observation we have radio afterglow fingerprints in the observations. But to modeling GRB, we need to figure out the GRB's progenitors. For long gamma ray burst, as we know, the host galaxy of star-forming dwarf galaxies, and in 1993, Worsley introduced a model for rapidly rotating massive stars and iron core collapse. Then we have black hole formation and fallback supernova. So we have a long gamma ray burst plus a weak supernova. But for short gamma ray burst progenitor, most of these short gamma ray burst host galaxies are elliptical ones with low star forming rate. This might strengthen the neutron star merging or neutron star black hole merging. For modeling both of these GRBs, we need to, any model need to figure out and answer this question. This model should be capable to produce jet and highly luminosity wavelengths, and also produce jet should be clean, namely the energy per baryon must be much more than MPCdo. Also, the model capable to get reactive the periodic and irregular manner, and also be able to stay active in long term. So hyperaccretion accreting black hole and magnetars, they are two promising candidates that fulfill these features. Hyperaccretion accreting black holes that we are trying to use it is a accretion rate around 0.01 to 10 solar mass per second accretion rate to produce GRB. High mass accretion rate is a very hot plasma, and in this case, because the accretion rate is so high, photon trapping occurs, and the disk unable to radiate away its energy. So efficient neutrino cooling comes to survive this model. So in this kind of model, this effectively cooling by neutrino coming out from the disk. And this plausible mechanism that may cause jet production. We have neutrino antineutrino annihilation, Blanford-Zanjek mechanism, and Blanford-Payne mechanism. Blanford-Zanjek mechanism is a mechanism what introduced by Blanford and Zanjek that in this case the process which through that the rotational energy of black hole can be efficiently extracted. In this case, we have force-free condition in the magnetic field, and the charged particle accelerated in this ways, and so we have strong jets. The other model is the fast magnetars that we are not talking about it. On the other hand, we have some non-electromagnetic radiation from GRB, is ultra high energy neutrino and also pressure neutrinos, and recently very interesting for the people to modeling GRBs that can reproduce gravitational wave. At first, I'm going to introduce neutrino-dominated accretion flow. In this case, neutrino should be produced and then cooling, help the cooling the disk. Neutrinos are generated through the neutronization and thermal emission. The several timeline is there is for producing neutrinos, electron positron pair annihilation, or nucleons, Vereshchagin emission, and plasma decay. Even from one of these lines, we have neutrino producing high energy neutrino that can go out and bring a huge amount of energy from the disk. The most In the other hand, we have some process to the other process such as ORSA process that reproduce neutrinos, neutrino electronic and antineutrino electronic. The cooling rate per volume for electron neutrino is like this, and in this formula, X nucleus comes from this formula. On the other hand, when we have lots of neutrino, and also we have neutrino opacity that comes from the inverse process of each neutrino emission mechanism, and also from the scattering of neutrino from the targets. Neutrino opacity formula is this, and on that one, the later consider neutrino opacity like this. Because of the limitation of time, I'm going to skip some part of calculation and just focus on the result. Neutrino-dominated accretion fluids formula and thermodynamics is in the literature is very well known. In the thermodynamics of the ENDAF, we have 4 parts for the pressure: gas pressure, radiation pressure, degeneracy pressure, and the neutrino pressure. That you may see P gas, P radiation, P degeneracy, and P nu. For P nu, we use U nu over 3. That comes from this formula. The energy balance in the ENDAF is considered as Q viscose, energy generated by viscosity. Some part of this energy goes to advection mechanism, and the other part goes to cooling by neutrino emission, where Q viscosity comes from this formula, and also Q advection and Q viscosity. This is the well-known formula of neutrino-dominated accretion fluids. At the first paper, we tried to modeling gravitational instability in neutrino-dominated accretion fluids. Normally, we expect that the GI, gravitational instability, make in spiral structure with dense fragmentation inside, then time variability accretion, and jet layer of different Lorentz force and episodic emission. Or even in outer this fragmentation, the time variability accretion disk will be induced, and also we have X-ray flares. But GI, gravitational instability, in the inner disk is also possible. Mashhad in 2007 have been proposed the gravitational instability in the inner part of the disk, and in this case, baryonic mass accumulation will be happened, and the fast accretion will start episodic prompt emission. So I start for our first paper, self-gravitating in magnetized neutrino accretion disk. We try to modeling neutrino-dominated accretion disk in the case of self-gravitating and magnetized one. The formula of the continuity and momentum equation is here, and as we see, we have extra term in the energy balance comes from the magnetic cooling, and the magnetic cooling comes from this formula. Also, we consider the polytropic equation of states in the vertical direction. The hydrostatic balance in the vertical direction is this, just we add self-gravitating term in the vertical direction. Psi is a piso-Newtonian potential. For investigating the gravitational instability, we need to start with Tumra parameter. This gravitational unstable if Tumra parameter are less than 1. In the magnetized case, the Tumra parameter formula comes from this formula that VR is the Alphen velocity. Self-gravity play an important role, but we need to take care about the magnetic field effect, because the magnetic field play an important role, especially this kind of disk are they are very effective in the highly ionized plasma. Magnetic field can play an important role in two cases. In large scale, by magnetic braking, and small scale by viscous dissipation. One of the most important magnetic effect of magnetic field in the disk is a magnetic barrier mechanism. Since the field lines are frozen in the disk materials, the viscous time T nu can present the time scale of the magnetic flux accumulation. So we have a MAD model, magnetically arrested disk, that the magnetic field in the inner part of the disk, like this, is very, very strong and start to stop the accretion material. For R greater than Rm, the flow is axisymmetric, while for R less than Rm, the magnetic radius, the flow breaks into bubbles and streams and velocity much less than the free fall. For the very small radius, the fight, it fades toward the black hole through the magnetic reconnection. By the way, we need to calculate Rm, then some time scale, diffusion time scale, and viscous time scale. For being in the magnetic barrier regimes, we need to have T diffusion greater than T viscosity. Fragmentation occurs when the QM is less than 1, and we can put this constraint in the time scales. And we have also neutrino and Blandford Pinel luminosity that will be calculated directly from Q nu and integrating over the disk surface. Blandford Pinel luminosity is one of the mechanisms that works when the magnetic field, we have magnetic field around the disk and can be calculated from this formula. Then we show our results. These figures. We plot self-gravity in a magnetized N-dart, contours of density for m dot 0.1 and 10. Left panel is 0.1 and 10 panel is right panel is 10 solar mass per second. 3 order of density highlighted by dash line. And in top panel, we have self-gravitating magnetized case. In the middle panel, we have just self-gravity. And in the bottom plane, we have just magnetic field, magnetized disk. Pink area that you will see here, they are represent the gravitationally unstable zone, these parts. We will see that they are in the outer part of the disk, when that we expect the self-gravity play an important role. Also, we plot magnetic field component. VSMG is the vertically self-gravitating and magnetized, and this dash line is a magnetic case. You will see that the magnetic component deviated from each other in the outer part of the disk, where the self-gravity play an important role. We have in 3 cases, in m dot is 0.1, m dot is 1, m dot is 10. When the accretion rate is increases, the deviation from the magnetized case and with the self-gravitating magnetized case is more visible. Also, we plot velocity vector field. This panel is a self-gravity plus magnetic field. This is the second one, right panel, is the magnetized case, and this case is just self-gravitating case. Also, for considering time scale, we plot viscous time scale and diffusion time scale, and for different accretion rate. It is visible that in the lower m dot, T viscosity is very less than T diffusion, which enhance the magnetic accumulation and the magnetic barrier. So in the other hand, in these figures, we plot contours of three different cooling rates: advection cooling rate over Q viscose, QB over Q viscose, and Q viscose, Q neutrino over Q viscose. In the panel A, left panel, self-gravitating plus magnetized, and the right panel is just magnetized. In R M dot plane, the boundaries of the dominance are shown by solid line. Green is, and the black boundaries, magnetic cooling dominate. This part, they are magnetic cooling are important. And purple is displayed the neutrino dominated regime, and orange the advection dominated regime. So we will find that in which regions and with which accretion rate we can consider neutrino dominated regimes or magnet advection dominated regime, or even magnetic dominated regimes. Advection cooling rate, purple, becomes more important when the self-gravity is considered, especially in the outer disk. And at the end, we plot luminosity, luminosity of Blandford-Pine and luminosity of neutrino cooling for different range of M dot. In both cases, are strong enough to power GRB jets. So we will be able to estimate the luminosity of the disk. How much I have time? I think I cannot finish on time. So estimate the observational evidence. We could estimate that this physics occur from around 250 seconds. I'm going to talk about the second paper that we are talking about, GRB variability and following gravitational wave induced in the gravitational instability of inducts. Motivation is the Mashhad paper. When magnetic field is less than 10^14 Gauss, energy and momentum transport by neutrinos could suppress the growth of MRI. This gives the birth of an accumulation of baryon matter into the inner dead zone. So when the dead zone achieved a large amount of mass becomes gravitationally unstable. It's very important because Mashhad shows that in the inner part of the disk, near the dead zone, we have gravitationally unstable regions. Being inspired this idea, we consider the inner region of the disk being self-gravitating, and the concentration of the neutrino viscosity most affect the factor to transport the energy and momentum. So we try to model this system by considering the gravitational instability inner part of the disk. At the first, we start to check the validity and to see is there any reasons for to be considered that. As you see in this figure, gravitational, this is, we plot the Tumre parameters in a very high accretion rate. The inner part of the disk becomes gravitationally unstable when considering the self-gravity. If the purple line is the self-gravitating file, and the green one is the non-self-gravitating. In the non-self-gravitating case, just the outer part of the disk becomes gravitationally unstable. And gravitational fragmentation could be calculated from this formula. Then we plot for beta viscous parameters. I will introduce in here, because there is a model for viscosity that comes from gravitational instability. In this in description, viscosity, a small scale fragmentation, and in the disk will induce a turbulence that can make the outward transportation of angular momentum. So in a paper by Daschel, he introduced a new prescription for viscosity, which introduced by beta formula. We add the beta formula in the main momentum equation, but we will find that the regions that the disk will be gravitationally unstable. Accretion, the fragment of the observation evolution, we need some I'm taking the time, I take care of the time. In order to fragment the start accretion to the center of gravitational force, we need to take care this criteria. F and U is the shear force, FAT is the tidal force, and the F is self-gravitating. In this criteria, we have fragmentation will be a starts. So in this case, we will introduce L gamma, the consequence gamma ray luminosity owning the fragments. We plot many data. This is the observational data, and this is the linear fit. We plot gamma ray luminosity for given set of parameters, different range of m dot. The top panel, top left panel, black dot dash curve is the best fit line in our data, and the middle, the right panel is a different fit for various quantities of beta parameters and m dot. Eventually, as beta decrease, the fit to be data much more better with the phenomenological finding. And the lower bottoms, TSC versus we plot characteristic time TSC with L gamma, which as a set of various mass accretion rate. The fit, their fit is very good, are very good agreement with the observation. One important point is that when we have a fragmentation in the inner part of the disk, we will be able to calculate the possibility of gravitational wave comes from these parts. Oh, seems the time is limited.
Yes.
Okay. The characteristic strain in terms of frequency for source of distance 100 parameters is calculated. We plot here for two solar mass per second and 5.5 solar mass per second. In bottom in this panel, the noise amplitude HN for different detector are depicted through the color curves here. The area in pink here demonstrated our model estimated for a strain amplitude for a source at distance greater than 100 megaparsec. For comparison, data for compact binaries in spiral here in the bright purple have been shown. I'm trying to, I suggest to skip the third paper, that viscous evolution of magnetized clamp, because in this paper we try to modeling X-ray flare is quite different with that first paper. I stop here, and if is there any question, I would be glad to answer. Thank you for your attention.
Thank you, Professor Abbassi. If we have questions, let's have one short question, please.
Hi, Shahram. Can I ask a question?
Yeah.
Thank you so much. My question goes back to the metric you used for your analysis, and what method did you use to draw the shapes and diagrams for the components of the force-free field, force-free magnetic fields? Because we know there is no any exact solutions for such components. So which results do you use to plot them?
The detail is we didn't solve it, but we used the well-known solution for the magnetic field. It's just it was an assumption. I need to.
Sorry. Let me explain my question. Yeah. When you have an accretion disk around a black hole, what is your black hole? Which black hole do you use?
We use the non-rotating black hole, and we use Peso-Newtonian. We use the Peso-Newtonian potential, not relativistic one.
Okay, because if you want to extract the angular momentum and also the energy from the black hole, you have to use some rotating sources, rotating black holes.
I know that there are some relativistic solution, but we use the classical one.
But you say you use the Blanford-Zanegic mechanism, which recently the EHT team, the Event Horizon Telescope team, used this mechanism to extract that beautiful figure from the shadows and also the black hole 2 years ago. So how we can compare these results with observations? Because you say you didn't use any relativistic sources.
Yeah, actually, several assumptions have been proposed. One of the assumptions is that we use the Peso-Newtonian potential. So on the other hand, we don't any angular momentum communication between the disk and the central engine. And just we used Blanford-Payne and Blanford-Zanegic luminosity to calculate just the formula for a possible mechanism for cooling the disk, a jet. Because if you want to calculate.
So it's interesting.
I'm sure you can have this discussion further on separately from the meeting.
Okay, sure.
We have no time for questions. So let's thank the speaker again, and we can pass to the next speaker of this session, which is Dr. Laura Becerra, and she's going to speak about soft particle hydrodynamic simulation of the induced gravitational collapse. Therefore, please, Laura, the stage is yours.
Okay, can you see my screen?
Yes.
Okay. Hi, everyone. Well, as I said, I'm going to talk about the SPH simulation of the induced gravitational collapse. This work was part of my PhD thesis, was done with the supervisor Jorge Rueda, and in collaboration of Chris Fryer and Calora Ellinger from Los Alamos National Laboratory. Well, the induced gravitational collapse was a model to introduce to explain the connection between GRBs and supernova of type 1c. The progenitor of this model is a binary system formed by a carbon-oxygen core that is a star that have lost its hydrogen and helium layers from the binary interaction of its companion. Its companion is going to be a neutron star. And when the carbon-oxygen collapse and explodes in a supernova, the material ejected in this supernova is going to be gravitationally attracted by the neutron star companion, and this triggers a hypercritical accretion, and depending on the initial binary parameters and the properties of the supernova, the system can have mainly two different outcomes. In the first one, that we call them binary driving hypernova, the accretion of the neutron star companion is enough to make it reach its critical mass and collapse to a black hole. The icon of, in this case, is going to be a binary system of formed by the black hole and the neutron star that is the remnant of the collapse of the CO core. And in the other case is the accretion is not enough to trigger the collapse of the neutron star, we're going to have a binary system formed by two neutron stars, one more masses due to accretion from the supernova material than the others. And in this case, we have an X-ray flashes that are less energetic events. So what we want to do is to identify the parameters of the initial binary system that can favor the collapse of the neutron star and form the black hole with the emission of the GRB. So for this, what we want to model is the expansion of the supernova and the accretion of the material from this supernova on the neutron star companion. So we're going to have a binary system formed by two stars, the remnant of the CO core, that is, we're going to call it the new neutron stars, and the neutron star companion, and also we have the supernova material that was ejected from the collapse. This binary system, we're going to define a minimum period for this binary system, and this is defined as the minimum separation the CO cores and the neutron star can have in order to not have Roche-Loff overflow at the beginning of this kind of events. So for model this system, we're going to use a small particle hydrodynamic code that was developed at Los Alamos. In this code, basically, we're going to take the supernova ejecta and divide it in particles. Each of these particles have an assigned mass and an assigned position and smoothness. And with these three quantities, we can interpolate to define the physical quantities that are the density, pressure, internal energy, and so on. And for each of these particles, we're going to solve the aerodynamical equation, that is the mass, momentum, and energy conservation equations. And finally, to model the accretion of the neutron star and the new neutron star, we implement an accretion theorem. So each particle that coincides an accretion radius and the gravitational energy is less than its kinetical energy, and its momentum, its angular momentum is less than the momentum it will have if it's rotating around a Keplerian orbit. Is a particle check this twist condition, is going to accreted by the star. So this particle will be going to remove from the simulation, and the mass, linear momentum, and angular momentum will be going to zoom to the accreted object in order to conserve these quantities. And for the initial setup, we're going to take the pre-supernova progenitor from the Keplerian code and then collapse it with a one-dimensional code. And when the radio short reaches the surface of the CO core radius, we're going to map this 1D configuration to the 3D configuration for initialize the SPH code. So for example, here we got different density and velocity profile for different kinds of progenitors with different initial 0s main sequence initial mass. So we resume here the characteristics, the properties of these progenitors, and then we can start to simulate the induced gravitational collapse. So we start with a progenitor that has a 0s main sequence mass of 25 solar masses. So for this progenitor, the mass ejected in the supernova is around 5 solar masses. And the remnant object that, as I said, is going to be the new neutron star, has initial at 1.85 solar masses, and we assign a neutron star companion of 2 solar masses. The minimum orbital period for this numbers is going to be around 5 minutes. And the simulation will have 1 million particles. So here we have snapshots of the density in the equatorial plane of the binary system. At the center, we have the neutron star companion, and along the s-axis, we have the new neutron stars. So here is the equatorial plane, and here is a plane perpendicular to it. So we can follow the evolution of the density at different times. At the beginning, the faster layers of the supernova are going to pass the neutron star companion without being affected by this gravitational field. But when the slower matter approach is going to start to be captured by the neutron star, you see that it's formed like a tail, and then it start to form a disk around the neutron star. At the same time, at the beginning, in the new neutron star, the material that doesn't have enough kinetic energy to escape its gravitational collapse is going to make fallback. So we're going to have also accretion in the new neutron star. But also at some point, the material that was gravitational captured by the neutron star companion is also to be going to start to be attracted by the new neutron star. So we're going to have like a bump in the accretion on the new neutron star. So this is a 2D view of the system, and here is a 3D view of the system. Here we see the disk around the neutron star companion, and the material that I also going to the new neutron star. So we see that the initial spherical supernova is going to become asymmetry due to the presence of the neutron star companion. And to confirm the formation of the disk around this star, we have here the profile of the angular velocity of the particles close to the neutron star, and we see that close to this star, this particle follows a Keplerian orbit around it. And here we have the accretion rate of the neutron star companion. The neutron star companion, we see the accretion is peak at the beginning and then goes down at the times. Also, we got the accretion of the new neutron star, and we compare it with the accretion it would have without the presence of the neutron star. So in the black line, we just have the fallback accretion of the material that hasn't got enough energy to escape the gravitational collapse of the new neutron star. And we see that when it has the neutron star companion, at the beginning is the same fallback accretion, but at late times is produce like a bump in the accretion, and this is correspond to the moment it start to accrete the material that was captured by the new neutron star. So we also can notice that these accretion rates are of the order of 10⁻³ solar masses per second. So these are super Eddington accretion rates. In this case, the material, the photon are going to be trapped in the trapping radius, and so the gravitational energy are going to be emitted by neutrino emission. And the most efficient mechanism for this kind of scenario are going to be the annihilation of electron apposition for the neutrino emission channel. So now that we have the first simulation, we can systematically change the initial condition and see how this fate of the system is going to be affected. So we start to changing the energy of the supernova. So for this, we scale the initial kinetic energy and internal energy by a factor, in this case, less of 1. So the eta equal 1 is the most energetic supernova, and eta equal 0.7 is supernova less energetic. So as we suspect, in this case of less energetic supernova, the new neutron star companion is going to accrete more mass. But this is not going because it's increased the accretion rate, but it's increased the period of this accretion that accrete at a constant rate. So the change is not in the peak of the accretion, but more in the shape on the accretion rate. And in the case of the new neutron star companion, we see that at the beginning, for all the energy, we got more or less the same fallback accretion, but we have the bump during the late bump is early and bigger for less energetic accretion than for high energetic supernovas. So less energetic supernova will favor the collapse of the neutron star, and maybe also will favor the collapse of the new neutron stars. But if the supernova is not so energetic, all the material or most of the material are not going to be ejected, and maybe all the material going to probably going to do fallback, and we only have the collapse of the new neutron star. So here is a snapshot for the density of the simulation I just showed you, the more energetic supernova and with less energetic supernova. In this case, we see that in both stars, the new neutron star and the neutron star companion forms like this around them. And now we can also change the initial orbital period of the initial binary system. So we start with periods around 5 million. We increase them to 9 million and 12 million. And we see that in this case, for wider initial binary system, the accretion is going to be reduced as expected in both cases where the energy of the supernova is high or not so high. But we see that is more or less is a scale, and the LED accretion is followed like a power law expression. And we change the initial orbital period, but we can also change the initial mass of the neutron star companion. So in this case, we see that the accretion is less sensitive to the initial mass of the neutron star for the both energetic supernova that we have been working, the high one and the not so high one. But also this system allows us to study the binary system fate. I mean, if the system after the supernova event is remain bound or it remains outbound. And in this case, for example, we see the evolution of the orbits from the binary system center of mass reference frames, or for the simulation reference frame that is the center of mass of the initial binary system. And we see that in this case, for the period of around 5 million, independent of the energy of the supernova, the system always remains bound. And well, we know that in the case of binary system, if one of these stars go to a supernova event and the ejected material is instantaneous, we know that if the material ejected is more or less the half of the initial total mass of the binary system, the system is going to disrupt. But in the case of the binary or the induced gravitational collapse, this assumption doesn't apply because first, the supernova event is not instantaneous, and second, because the neutron star and the new neutron star cannot read mass from the supernova. So this is going to reduce the mass loss of the system. And for example, if we change the binary period of this system for longer binary period, we're going to have a period from which the system is going to remain unbound. So we here see that this period is going to be longer for the case of less energetic supernova than from the case of high energetic supernova. So in binary period, the parameter space of binary period is reduced for high energetic supernova in order that the final system remain bounded. And also we can change the CO core progenitor. As I told you at the beginning, we can have a progenitor of different 0s sequence initial masses. So here we work with 15, 25, 30, and 40. And in all the cases, we can play with the initial energy of the supernova, the initial binary period, and the mass of the neutron star companion. And more or less say, do the same conclusion. For example, here we got the case of the 30 solar masses, 0s sequence progenitors. We have a high energetic progenitor, and we see how the material, because it's so energetic, the neutron star is not going to capture, or not going to be able to capture the material that pass it from the supernova. More of the material will pass without being affected by the presence of the neutron star. In this case, the accretion is going to be low. And on the other hand, if we have a less energetic supernova, too less of the material is going to do fallback, and we see that the new neutron star and the neutron star companion will accrete material from the supernova. And if we scale the energy of the supernova, we can move to one regime to another. For example, if we reduce the energy from a high energetic supernova, we see that when we reduce it, we form the disk around the neutron star, and then around of the new neutron star. Or in the other case, when we have a low energetic supernova, if we decrease this value, we increase this energy, we will have the same effect when all the material pass the neutron star companion without being affected by it. And now we want to calculate or to define whether the neutron star collapse or not from the accretion of the supernova jet. And for this, we need to follow the mass, or the neutron star gravitational mass, and the angular momentum of the neutron star. So for the neutron star, we're going to assume that the baryonic mass of the accretion rate that we get from the simulation is going to be the baryonic mass accretion rate on the neutron star. And as we can see, the material before being accreted to a neutron star, it will form a disk around the neutron star. So the angular momentum that will going to be accreted by the neutron star is the one of the last stable orbit of the neutron star. And we're going to assume that the neutron star will follow an evolution through a stable configuration. And we're going to use the uniformly rotating configuration made by Chipolletta. These configurations are done with a general relativistic code. And from this configuration, we can get the relation between the gravitational mass and the baryonic, the relation between the gravitational mass, baryonic mass, and angular momentum of the neutron star are also we get a relation of the last stable orbit of the neutron star. And we define some limits for the critical mass of the accretion of the critical mass of the neutron star. We have the mass shedding limit when is the particle at the surface of the neutron star rotates faster than the centrifugal force equals the gravitational force on the surface of the neutron stars. And we also have the secular instability limit, that is when the neutron star becomes unstable to axial symmetric perturbations. So we can integrate this equation with these assumptions. And for example, if we assume that all the angular momentum of the particles that the neutron star accrete is gained by the new neutron stars, we see that in this case, all the neutron star and the neutron star companion reach the mass shedding limit in a short time, right? But this doesn't consider that it may be loss of angular momentum due to the jet material jets or some outflows of the system. So if we consider an efficient parameter and there is accretion from the disk, if we consider an efficient parameter of 1, we see again that just the neutron star companion reaches the mass shedding limit, but we see that the new neutron star remain stable for all the simulation. But if we consider a less efficient parameter, let's say 0.5, in this case the neutron star companion will reach the secular instability limit and collapse to a black hole. And the new neutron star companion will reach the mass shedding limit. So we do the same exercise for all the configuration. We take the high energetic supernova. For a high energetic supernova, all the cases, the neutron star and the new neutron star remains stable. Well, the new neutron star remains stable, but the neutron star for efficient parameter of 0.5, we have cases where the high energetic, the neutron star reach the secular instability limit, and when the accretion is more efficient, we just one case when the neutron star companion reach the mass shedding limit. So this analysis also has a consequence in the GRB analysis made by the group. For example, these GRBs have been identified with different initial binary systems. For example, this is GRB where a binary driven hypernova example where the neutron star collapse to a black hole. These events have been identified with an initial binary period of 5 minutes, where the progenitor, the CO core progenitor was the 25 main sequence, 0H main sequence progenitor. And this one is an X-ray flash example where the neutron star doesn't collapse to a black hole, and in this case, the progenitor is the same one, but the initial binary of the system was around 12 minutes. So, thank you for your time. Questions?
Thank you very much. And
thank you, Laura. There is time for a couple of questions. Probably Professor Ruffini would like to ask one.
well, what is very interesting is to look for different mass of the supernova, different energy of the supernova, and see how the new neutron star spinning up is a function not only of the binary period, but also of the energy of the supernova. And we have to see in your many computation, if you have considered this case of different binary period, but a different energy of the supernova and the effect on the new neutron star. Of course, always the collapse of the companion star will happen, but the spinning up of the new neutron star, this is the delicate parameter.
Yes, actually, well, we also here model the spinning of the new neutron star is in red, and it's going to depend of the accretion, and the accretion is depending also on the supernova, the energy of the supernova explosion, and different energy we're going to have different fates for also the new neutron star.
Yes. This is the key quantity we would like to obtain from your simulation. How the spin up of the new neutron star changes as a function of the energy of the supernova, of the supercore. And if you can indicate us some cases, that will be very nice. And of course, I congratulate you for this many years of work and simulation, which have been essential for guiding us in the VDHL model. But now we are coming to a very fine structure, which we are fitting with the latest data.
Okay, thank you, Laura. Once again, we have to move to our next speaker. Last speaker of today's presentation is Professor Shadi Tahvildar-zade, who is connected already, and he's going to speak on the role of general relativity in the structure of elementary particles of matter. Shadi, can you hear us?
Yes. Can you hear me?
Yes, yes, please. Can you share your screen now?
Sure, I'm doing. Okay. Is this visible?
Yes, we can see it. Confirm.
All right, great. So thank you so much for inviting me to this conference. I'd like to talk about some results that we have with our, here's a list of my collaborators, my longtime colleague, Michael Kiesling, my former student, Maulik Balasubramanian, now a colleague at Rutgers, our postdoc, Eric Ling, current postdoc, a former postdoc, Ebru Toprak, now at Yale, and former postdoc, Annegret Burcher, now at a professor at in Radboud University in Nijmegen, Holland, and former student, Eric Amorim, now a postdoc in Cologne. So, more than 100 years ago, Einstein posed the following question in a paper entitled Spielen Gravitationsfelder im Aufbau der materiellen Elementarteilchen eine wesentliche Rolle, which translates to, does the gravitational field play an essential role in the structure of the elementary particles of matter? I don't think Einstein actually answered this question in this paper, but obviously it's a very important question, and I hope to convince you by the end of this talk that the answer is yes. To start off, we're going to look at the toy model for a joint evolution of a field and a particle, in which I'm going to think about a very simple field. This is just a scalar field in one space dimension, which is sourced by a delta function concentrated on a trajectory of the singularity of this field. So I would like to identify the singularity of the field with the particle. So this is the equation for the evolution of the field, and we would also need equations for the evolution of the particle, and that would be the kind of problem that we would like to study. So notice that here the blue parts, V0 and V1, are smooth, compactly supported away from where the singularity is. Here's the initial singularity. So that what we want to have in mind is that we have a particle that's at rest at the origin, and some radiation comes in. The radiation is modeled by this V0 and V1, and it jiggles the particle, and then the particle does something afterwards, and we would like to know what happens. So to complete this picture, we also need equations of motion for the singularity itself. We are going to take the Newton-Einstein classical relativistic equations. So you have Q is the position and P is the momentum of the particle. So velocity is related to momentum by the usual relativistic relationship. Here, the speed of light is equal to 1. And then the derivative of the momentum is, of course, the force on the particle. And this force presumably depends on the field, and we need to find what this force is. Now, in 2020, my colleague Michael Kiesling showed that one can use momentum balance law to find an expression for this force on the particle. So this, I will describe this procedure in a little bit later, but here what we get for this particular example, we get that this force on the particle is related to jump in the certain field-related quantity. So more specifically, the jump in the momentum density of the field times the velocity of the particle plus the jump in the stress density across the trajectory of the field. So this is the kind of relationship that we would like to be able to derive in much more general and generic situations. Now, one thing that is interesting here is that in this particular case, you can solve this equation, of course, because this is just a linear wave equation, and you can plug what you find for u in here and evaluate the force term. And when you do that, you get two terms here. The first term is not a surprise. It looks very much like a Lorentz force. It's the minus the gradient of v, so where v is the to the radiation part of the equation, homogeneous equation, a wave equation with the initial data. So this part, it looks just like charge times the electric field, so to speak. But then there is a second term, and this second term is the self force, which, as you can see, it's proportional to the momentum of the particle, and this term survives even if v is 0. So that's interesting. So this is where you're first, for the first time, you're seeing some finite expression for the self force that's actually doing something here. So now once the bottom line is, once you have an expression for F, you have a joint evolution of the field and the singularity of the field treated as a particle. So this goes back a long time to the idea of one can think of matter particles as singularities of a space-time, goes back to Weil, and Einstein was himself a subscriber to this idea for some time. He later changed his mind. But meanwhile, Einstein worked with Infeld and Hoffman, and he wrote a series of papers in which they tried to do something similar for Einstein's equations. They tried to, in fact, derive the equations of motion for the particles from the field equations themselves. And of course, this is not what I did here in this example. I sort of postulated these equations separately. Einstein and Infeld Hoffman were hoping to derive those equations from field equations, and this was less than successful. However, now there is a new approach. It started with Kiesling, and now Kiesling and myself. And the new approach is the following. We start with assuming that the field equations are derivable from an action principle. This is a very reasonable assumption. All fundamental physical laws that we know of are derivable from action principles. If that is the case, then there is this object called the energy momentum tensor that satisfies a conservation law, of course, away from the singularities where this differentiation makes sense. So now, suppose we are in situations where this energy tensor can be continued into the location of the singularities. This won't always be the case, but there will be situations where the singularities are just right and they allow us to continue the energy tensor into the location of the singularities. In that case, the total energy tensor can be written as the field tensor plus a singular part that's concentrated on the trajectories of the particles involved. So if we have such a situation, and moreover, there's another if here, if this total object still is divergence-free in some sense, of course, this has to be in the sense of distributions because this is no longer a classical, you don't have the derivatives needed to make sense of this. But suppose this relationship for the total energy tensor still holds in a weak sense, then you can still use the momentum balance law to find the force on the particle. And here's how it goes. So we all know, so the divergence of the particle energy tensor is the force, and because the total divergence is 0, this is equal to minus the divergence of the field energy tensor. And now you can integrate both sides of this, use a divergence theorem, and conclude an expression like this, which says that the force is equal to minus the time derivative of the total field momentum. So there is one important caveat here in this formula, and that is that this integral must exist, and therefore this procedure succeeds only if the field momentum density is integrable in a neighborhood of the singularity. And it will turn out that in many situations of interest, this is actually not the case. And therefore one has to do something else about this. But if the field momentum density is locally integrable, one can always find a force on the particle, and therefore one is ready to study the joint evolution of fields and the singularities of the fields. Okay, so what you may ask at this point, how do we know that this object is still divergence-free? Because previously there was a proof of that, right? But now this is this more generalized object, and we don't know, there is no guarantee that this would still be divergence-free. It would make sense for it to be the case, but we don't know if it is. Now it's where the gravity comes in. Suppose Einstein's equations are satisfied, which says that the Einstein tensor equals coupling constant times the total energy tensor. And suppose this, so if this equation holds in some appropriate sense, and now we want to conclude that the divergence of the right-hand side is still 0, well, we need to know that the divergence of the left-hand side is 0. If things were smooth, if there were no singularities, that's an identity. It's called the twice contracted second Bianchi identity, says that for all metrics, regardless of whether they're solutions of Einstein's equations or not, this divergence is 0. Now, if this is still the case, at least in a weak sense, then the divergence and Einstein's equations hold, then the right-hand side also holds in a weak sense, and we are ready to go. So here's how gravity can play a role. But we asked, what are the conditions on the space-time metric that would guarantee this weak second Bianchi identity holds in a neighborhood of the space-time? For the special case of a static, spherically symmetric space-times with a central time-like singularity, we have an answer, which is in terms of the mass function. I remind you the definition of the mass function for a spherically symmetric space-time is as follows. There is this coordinate called the area radius coordinate, which you have for spherically symmetric cases. And you form this expression, 1 minus the inner product of the gradient of R with itself times this factor. And this is a mass function. And in this theorem with Becerra and Kiesling, we showed that twice contracted weak second Bianchi identity holds in the neighborhood of the R equals 0 if the mass function has a certain expansion of the following form, where the constant term is either negative, or if the constant term is 0, then the coefficient of R is sufficiently small. So that sort of gives at least the criteria. Of course, this is not an if and only if. This is a sufficient condition. And there is still much work remain to be done to figure out, to be able to answer this question in more generality. But this is obviously a start. Now, just remind you, where does this identity comes from? So you have something called the second Bianchi identity that's satisfied by the Riemann curvature tensor. This is this thing here. You contract it once with the metric, you get an identity satisfied by the Ricci curvature. And if you contract again, you get this thing. So this is the twice contracted thing. And the thing in parentheses is precisely the Einstein tensor. So the weak version of this is you multiply this by the gradient of an arbitrary vector field and you integrate by parts, and you insist that instead of this expression holding pointwise, this integral is 0 no matter what vector field you put in here. So that would be the weak version. That's what I mean by the weak version of the second Bianchi identity. Let us remind ourselves of some of the properties of the mass function. The mass function at infinity, it gives you the total mass, the ADM mass. It is related to Hawking mass. If you look at a sphere of radius r, and you look at the sequence of surfaces that are shrinking down to that sphere, and you look at the Hawking mass, which is defined for closed surfaces, two surfaces. If you look at the Hawking mass of that and take this limit, this is precisely this function, gives you this m of r. Now, you can take this function and you can take its limit as r goes to 0, the limit from the above, and this number that you get here is called the bare mass of the singularity at r equals 0. This is a number that can be positive, negative, or 0. It could be infinite. If this number is positive, it's easy to see that the singularity is going to be shielded by an event horizon. And that's not the case of interest here, because we are trying to model particles, as you will see. So we were going to take this number to be less than or equal to 0. Here are some examples. If you have a Schwarzschild black hole, this mass function is just a constant. It's the positive constant. The negative mass Schwarzschild, which is also a solution of Einstein's equations, is in that case, m of r is a negative constant. And this is, of course, a naked singularity case. The solution, the spherically symmetric solution of Einstein-Maxwell, the charged version of Schwarzschild, is called Reissner-Weil-Nordström. And the mass function for that is m minus q squared over 2r, where m is the total mass and q is the total charge. And in this case, you can see as you take the limit going to 0, the bare mass is minus infinity. This case, you can have either naked or black hole regimes for this space-time. But if you are thinking about elementary particles and you stick in here for Q, the charge of an electron, let's say, and for M, the mass of the electron, you will see that you are deep within the naked regime and not the black hole regime. And that's why I was referring to, that's why before I said we are not interested in the black hole regime of these solutions. Now, here's a prototype of a space-time of a point charge where m could be a C2 function of r, which has a certain expansion as r goes to 0, and an asymptotic expansion as r goes to infinity. And the only main condition we have is that this constant m is not being negative. So examples of a space-times where weak second Bianchi identity is not satisfied is Reissner-Weil-Nordström. Examples of those where it is satisfied is Hoffman's space-time. So Hoffman's space-time is a solution of Einstein-Maxwell when you use the Born-Infeld law of electromagnetism instead of the usual Maxwell law. And when you do that, you get this mass function that has the right behavior, and more generally, this holds for electrovacuum spacetimes when the reduced Hamiltonian, which is this function zeta here, behaves like a square root of its argument as mu goes to infinity. And of course, when you try Maxwell's linear law of electrovacuum, when the E is D and B is H, you get that this zeta of mu is just mu. And it doesn't, therefore, is very far from being like a square root of mu. So there's no chance for what we want to be true. So there are other electromagnetic vacuum laws as Born-Infeld, and also what is known as Bopp-Landé-Thomas-Podolsky, which is a linear law but higher order involving the derivatives of the fields. So, and it's of interest for these things to see what happens in that case. Our student Eric Amorim proved that the static spherically symmetric solution to Einstein-Maxwell with the BLTP law exists. And what we want, the next thing to do is to find a two-point charge solution of these equations, which would no longer be spherically symmetric, but is still axisymmetric. So one hopes that one can make some progress in that direction. And this would be very interesting to see how electromagnetism and gravity could possibly be unified, at least in this sense. So now moving on to quantum physics, one can also do test this question of Einstein in the quantum realm. We can, for example, take a single electron and place it in the electrostatic and gravitational field of a much more massive charge, which would represent the nucleus. And we can model the nucleus as the central singularity of a static spherically symmetric electrovacuum spacetime, and study Dirac equations on that background. In particular, we can put Dirac equation on the Hoffman spacetime with zero bare mass, and this was shown by my student Balasubramanian, that the Hamiltonian in that case is essentially self-adjoint. The continuous spectrum has a gap, as it's expected to do, and there are infinitely many eigenvalues in the gap. So everything seems to fit the narrative that we want, and yet we are in this case where there is, when we have gravity. Now, Bianchi turns out to be not the only factor. In fact, we showed with our postdoc Toprak that on any static spherically symmetric time with M0 negative, the Dirac Hamiltonian has uncountably many self-adjoint extensions. So we are losing essential self-adjointness. But if one finds a criteria to distinguish one of them, then that's still interesting, because any of these extensions have the right continuous spectrum and have infinitely many eigenvalues in the gap. So more studies need to be made in that direction. And of course, Reissner-Weil-Nordstrom fits in here because its M0 is minus infinity. So this result was known about Reissner-Weil-Nordstrom. It goes back to Cohen and Powers. All right, now, another thing that is of interest, to look at, instead of point particles, one studies particles that have more structure, for example, ring-like particles. Now, in 1896, a long time ago, Sommerfeld looked at the generalization of Riemann surfaces to 3D. And he started by gluing two copies of R3, cross-gluing them across a disk, so the top of one disk to the bottom of the other disk of radius A, let's say. So you can do this, and after you're done, you get a three-dimensional space, which is non-trivial topologically. And this is actually the branched Riemann space. So in other words, the equivalent of Riemann surface for a particular solution of Maxwell's equations, which is called the Appel field. It was found by Paul Appel actually before Sommerfeld. So if you can add a time dimension to this, and you get a static axisymmetric space-time. Why is that important? You will see. The points on this ring are conical singularities for the metric. And the Appel field is such that this ring appears as positively charged in one sheet of the space-time and negatively charged in the other sheet. So why is that significant? Well, Kerr-Newman, you may know, is a stationary axisymmetric solution of Einstein-Maxwell. This solution has 4 parameters: the mass, the angular momentum per unit mass, the charge, and it, of course, it also depends on the gravitational constant, capital G. In fact, the way these constants appear in the metric of Kerr-Newman is in the following way. M is always shows up as G times M, and Q squared shows up as G times Q squared. So if you take the limit as G goes to 0, you get this space-time that I was talking about, this double-sheeted space-time. And the electromagnetic field that is already there on Kerr-Newman survives and becomes and is this Apple field that we're talking about. So this limit, this is called the 0G limit of Kerr-Newman. It's locally flat, but it's not globally. It's not Minkowski because it is double sheeted. It is topologically non-trivial, and it has this one parameter A remaining in it. So what we did with my colleague is we studied Dirac Hamiltonian on this space-time, and we showed that it's essentially self-adjoint, and its spectrum is symmetric about 0. The continuous spectrum is still what you would expect. And recently, with our postdoc Eric Ling, we showed that the discrete spectrum of this Hamiltonian consists of an infinite family of eigenvalues indexed by 3 integers, which accumulate at the endpoints. And in fact, because of this extra parameter that we have, the degeneracies normally in the Dirac equation break, and we get hyperfine splitting and Lamb shift-like effects showing up. So that is very interesting. That's another instance of what we think as an influence of general relativity, because notice all of this came out of the study of this Kerr-Newman space-time. All right, for my last topic today, I want to talk about an intriguing paper that my colleague wrote in 2018 titled "Do Particles and Antiparticles Really Annihilate Each Other?" So you can, this is posted on the archive, you can go and look at the details, but here's the basics. Positronium is the bound state between an electron and a positron. The binding energy of it is a few electron volts, and the lifespan of it is this, and it decays through annihilation, supposedly, to 2 photons. The effective potential has the following form, where n is the Bohr quantum number. So, and when you plot that, you will see that for n equals 1, you have a minimum at, at very close to 2 is the, here I'm setting mc squared is equal, these are in the units of mc squared. So this 2 is the free energy of 2 electrons, or an electron and a positron. And then here we have a bound state, which represents one version of the positronium. Now, this only includes the electrical interaction of the 2-point charges. But what if we also include magnetic dipole-dipole interactions? If we do include those, we see that the potential gets modified by adding a term that's proportional to 1 over r cubed, where r is the separation between the charges. So this potential is actually unbounded below. So for point particles, we are not getting very much out of this. We have to somehow figure out how to sweep this under the rug. But now what if we try ring particles instead of point particles? Very interestingly, if you replace point particles with ring particles and repeat this analysis, you get this potential, which looks kind of awful. It has all these elliptic functions in there, but then you can plot that, and what you see is that this looks superficially very similar to the previous plot, but now you have a very tight bound state, because this r distance is like 10 to the minus 5 in the units of the Compton wavelength of the electron. So it's a very tight bound state with very, very small energy. So this is like they are so close that they appear to have annihilated each other. And the bound state, of course, is going to be neutral and of spin 0. So it would hardly interact with matter except gravitationally and in bulk. So this could be the ultralight boson that you were looking for as the origin of dark matter in the universe, and Quisling has a proposal for an experiment to find evidence for the existence of these things. So to conclude, general relativity does play an essential role in the structure of matter, and for the following reasons. On spacetimes that are solutions of Einstein's equations, if the weak version of second Bianchi identity holds, momentum balance laws can be used to derive equations of motion for matter particles, which are identified with the singularities of the fields on that spacetime. Inclusion of relativistic gravity has a profound effect on the spectral properties of Dirac-Hamiltonians for hydrogen and hydrogenic ions. Non-trivial topology of spacetimes such as Kerr-Newman remain even after G is set to 0. The singularities of these multi-sheeted spacetimes can be identified with ring-like elementary particles. The Dirac-Hamiltonian for a single electron on these multi-sheeted spacetimes is well-behaved and captures all of the essential features one would expect, in addition to breaking the degeneracies in the standard theory, which leads to hyperfine splitting and Lamb shift-like effects. And finally, ring-like particles facilitate the existence of a true ground state of positronium, which could be the origin of dark matter in the universe. Thank you very much for listening.
Thank you, Shadi. Thank you for this illuminating talk. We probably have some questions since this is our last speaker.
Yeah, can I ask
Yes,
one question?
please.
I think this
Introduce yourself, please.
Yeah, my name is Maurice Van Putten, speaking from Seoul, South Korea. I think your talk is very interesting, and it's very tantalizing to think about bound states, but wouldn't you think there is potentially a dissociation in when exposed to very short wavelength radiation?
Well, it has to be very, very short length, because this is, as I said, the binding energy is quite large. So the energy is almost 0. It's like 10 to the minus 3 in this scale that I had. So, well, if you look at the ordinary positronium, it's just a few electron volts, but this is much, much smaller than that. So it will be very hard to. You will see the 2 photons coming out, and you know, it would not be so easy to figure out that whether this is actually anything remains there. So so I think that's the point. Therefore, this experiment that I was suggesting should look for looks for another signature. In fact, tries to look for 1 photon decays, and based on that. But of course, it's at this point is a matter of conjecture. One has to, more analysis is needed before one can say definitively how this is going to work out. But it is, as you said, is quite tantalizing.
Okay, thanks.
Other questions?
Can I ask my question?
Yes, please.
Thank you. If I understood correctly, you are more interested in bare singularities than those with event horizon, yes?
Yes.
So how one can overcome the Penrose censorship theorem in this regard?
Because it's not a theorem.
As you said, just
cosmic
a model,
censorship, yeah? I remind you, cosmic censorship is a conjecture.
Yes. So your model is just...
It does not say that naked singularities don't exist.
Yes. So you mean your model, as you said, is just a toy model, yes?
Which one? The one I first showed, that was a toy model. But when I'm talking about naked singularities, I mean, so just to confirm your suspicions, I am modeling elementary particles as naked singularities of a space-time. This is what Einstein, Infeld, Hoffman were doing. They were not saying it in so many words, but this is what they were doing.
Okay.
So in other words, time-like singularities of space-time. Of course, they have to be time-like. And if they are time-like, then they are naked.
And if we wanted to observe them, how we can?
I don't know.
Oh,
I mean,
okay.
observe
if
them.
You mean they are physical, if you mean
we are observing them. We are observing them. These are the particles, right? These are the elementary particles.
So how, which data you use to compare the results, theoretical result, and the observations?
But I'm not getting any different theoretical results than that different from what everybody else is getting. So let's say I am studying this Dirac equation, right, on this background, which has a naked singularity, and I'm getting very similar spectrum.
Okay.
To what you would get if you just put Dirac's equation on a Minkowski space and put a point charge by hand there, right? Of course, this is not surprising because you don't expect gravity to change the spectrum. Yes. What happens though is that when you use relativistic gravity, if you're not paying attention to what's happening, right? Like if you put it on Reissner-Weil Nostrom and so on, then you see that all kinds of things go wrong.
Okay, thank you so much.
Okay, thank you, Shadi. I think we have no more questions. Therefore, let's thank all the speakers of the afternoon session and all the speakers of today. And Sarush, please, if you want to say a few words.
Can I ask a question?
Well,
I think there's a question. I don't know.
Excuse
me.
Very short, can I ask a question?
Very short, please. Yes.
Yes, so it's very, very short. It's to Shadi. Is this these ring-like particle that you said implies a string theory?
Well, not really, because the string theory, these strings are in extra dimensions. These things are not don't live in extra dimensions. This is just in physical space-time there are rings. So it has the flavor of a string theory, but it's not the strings. The little loops are not in unobservable small dimensions. They're just in physical space-time. And I should have said that the radius of the ring turns out to be proportional to the anomalous magnetic moment of the electron.
Okay, but anyway, they are not point-like particles. Is it right?
They are not point-like anymore. That's right. They're ring-like.
Thank you.
So thank you, Shadi, and thanks to all the speakers. And actually, you know, in this three picture, we have 3 time zone. Shadi is in the early morning, you know, Gregory is in the afternoon, and we are going to the night. So thank you everyone for making this conference very amazing, and we hope to see you tomorrow. We will start at 10 a.m. in the morning in Iranian time and 7:30 at Central European time. And, you know, we have very great speakers tomorrow. We will start with Reuter, and then we'll continue with Yao, and we have so many amazing talks tomorrow. And we will see you tomorrow, and thank you, everyone.
We should find a way to let more time for discussion, because one of the best part of the meeting is the very nice questions that they are asking. Everybody's asking. Therefore, maybe we should strictly ask the speaker not to go over the 25 and really give the 5 minutes discussion lots of relevance. Even in this last talk, there are so many things to be discussed, and we will continue in different occasions. Well, I think I'm very happy of the progress we are doing, and look forward for tomorrow.
Yes, that's a great suggestion. We will do accordingly tomorrow. So let's finish the session here.
Yes. Yes.
Okay. So thank you, everyone, and see you tomorrow.